Hi all, and welcome to your second lesson for the week, and we're going to talk about something called the Pigeonhole Principle, which is actually one of my favorite weird rules when we talk about counting problems like what we've seen in this chapter. So get yourself ready for notes, and we're going to talk about the Pigeonhole Principle. So what this means in its most basic form is it says, suppose n objects are placed into k groups, then if n is greater than k for at least one group must have more than one object, and if n is less than k, at least one group must be empty. And so this is the idea of what are called pigeonholes, where pigeons used to live, and I'm just going to draw a little picture here that I'll erase in a second, is that if I have, let's say, 3 pigeonholes, or these are our 3 groups, and I have I have n is greater than k, so that means that I have more pigeons than I have groups or holes for them to go into. That every pigeon's going to go into its box. Oh, but there's a 4th one left over, so it's going to have to go in with a buddy. That's what this means. At least one group must have more than one object, so a group like this will exist. However, if there's 3 groups and only 2 pigeons, even if they all spread out, there's going to be an empty one. And even if they all join together, there's still going to be at least one must be empty. So this is one of those things in math that feels like maybe feels so rudimentary that it's obvious, but it can actually be a really powerful idea. And I'll show you a couple of examples for that, and then you'll, of course, work on some of your own in the homework. So number 1 says, show that if you pick any 6 digits, that 2 of them must add up to 9. So whenever we're looking at a pigeonhole principle, you always want to think about what your groups are. So in this case, we're thinking about digits that add up to 9. So my first group would be 0 and 9. Another group would be 1, 8, 2, 7, 3, 6, and 4, 5. So these are our groups that we have. We have 1, 2, 3, 4, 5 groups of 2 digits that add up to 9. Now, you'll notice again, I said that there are 5 groups. And since it says here that we're picking 6 digits, even if I pick 0, 1, 2, 3, and 4, the 6th one I pick has to be one of the other pairs. It has to be 9, 8, 7, or 6, in which case they would be in the same group. So this is a pigeonhole principle problem. Show that if you pick any 6 digits, well, we have 5 groups that add up to 9. So if you select 6, one group has 2 members in it, and those 2 numbers add up to 9. If you want to see a more written out explanation for this, please look at the attached PDF, because taking the time to write that out is just going to make this video really long. So if I'm looking now at number 2 says, show that, and here we have our symbolic logic, show that for all a in the natural numbers, there exists a k and l in the natural numbers, where k is not equal to l, such that, st, a to the k minus a to the l is divisible by 10. So here we're starting to get into some very complicated proofs. One thing that I'm always going to recommend with the symbolic logic is that you start out by writing it in sort of colloquial English. So for every natural number, there exists a k and l in the natural numbers, such that the difference is divisible by 10. So again, we're going to think about groups, and whenever you see a divisibility problem, the best option for the different groups is based on the remainder. So when we talk about things, we're going to say remainder 0, and this one is nice because this just means that it is divisible by that number. So if I do a division problem with dividing by 10 and I get a remainder of 0, this just means it's divisible in this case by 10. though of course this would be a similar problem to whatever you're using. So we have a remainder 0. You could also have a remainder 1, a remainder 2, 3, 4, 5, 6, 7, 8, and 9. And notice I stop here, because if I have a remainder 10, that means that it's just going to evenly divide, because remainder 10 would be divisible by 10, and it goes back up into this group. And then the process will start all over again, because we have a divisible number, and then as we count up, that would have a remainder 1, remainder 2, remainder 3, and so on until we hit 10 again, and it goes back to the beginning. So these are our groups where we're talking about remainders, and if we can count, we can see that we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 groups. So this is 10 groups, so this is our, think about this as our K number. Now, it doesn't tell us to select a certain number here, but what we can do is if you select any 11, whoop, that's not how we spell. And I'm picking 11, of course, because it is more than 10. Any 11 powers of A. And since there are absolutely more than 11 numbers in the natural numbers, that's going to be just fine. If you pick any 11 numbers, powers of A, 2 of them will have the same remainder. And this is because of the pigeonhole principle, right? If we pick any 10, they could all have different remainders, and that would be absolutely possible. But if we pick the 11th, it has to have a buddy. Now, and here's the important thing with divisibility, is that if I have remainder x, and we take another number minus remainder x, those will cancel out and be remainder 10. Because, remainder 0, which, as we talked about, means that they are divisible by 10. So that pair of powers with the same remainder is our difference that's divisible by 10. Again, if you want to see a longer, more written out one, please look at the PDF. Our last example is a geometry problem, and you will also see these with pigeonhole principles. So for number 3, it says select any 5 points in a square with a side length of 1 unit. Show that at least 2 points are, and this is a typo I want to change, not closer, but are within. So closer or equal to. There we go. So are within root 2 over 2 units. So sometimes with this, I find it helpful to draw a picture. So if I have this picture here, and the idea is that if this is a side length of 1 and I pick any 5 things inside here, that they have to be within root 2 over 2, 2 of the points. So for example, here I can look at for the closest to, oh, here, that's going to be true. Now the question becomes, how do I know this is true? Well, one thing that will often be true about problems with geometry and this idea of proximity is ask yourself, what are the farthest away the points can be? So the farthest let's start with just 4 points, are the corners, right? If it was farthest 2 points, it would be opposite corners. But then as we throw in 2 more, we're going to have corners like that. Now, when we put in the 5th number between all of these, we have to ask ourselves a little bit about where, because we don't have any corners left, obviously. If we put it here, that's a 1/2 to 1/2. Granted, it's far enough away. And what you realize is that the next farthest dispersed would be right here in the middle. So there we go. So now we have these are the most dispersed, right? The most spread out 5 points in a square. Now we ask ourselves, how far away are the most dispersed points? Well, we know that this is 1, so the whole diagonal, using our Pythagorean theorem, our special right triangles, would be root 2 times 1, or just root 2. So then this is where the root 2 over 2 comes in, is it's half of this distance. Right? So now we know that the most dispersed 5 points are, at least root 2 over 2 away. But if we move this any closer, it becomes closer to this one. If we move it at all, it becomes closer here or here, here. If we move it away from one point, it's going to move closer than root 2 over 2 from the others. Therefore, if you picked any other set of points, any other points will also have at least two, because if we move it, like let's say we move this point over here, it's now farther from these two, but it would be closer to these two. So it's not guaranteed that they'll all be within root 2 over 2 of each other. But there will have 2 that are no more than root 2 over 2 units apart. All right, again, I recommend for this one that you definitely do look at the PDF as well as the video. And if you have any questions, please leave them in the comments or nominate any homework questions that you want to see addressed. I'll talk to you later.